till rate matching. Okay, so we have understood. Sorry. So we understood what was rate matching, and we had quite a bit of discussion on that. So today we'll go forward and look at the other blocks, and I think we should take about 10 minutes or so to finish the other blocks. They're not so complicated. And then we will start a little bit of MIMO and introduce you what is MIMO and other things. And then we'll look at more from a spec perspective. Okay. So after rate matching, the next thing that happens is something called bit interleaving. Okay. So what happened till now? Till now we had code blocks. We have segmented transport blocks into code blocks. Each code block has been LDPC encoded. After LDPC encoding, we do rate matching. Okay, so as to get enough number of bits, exact number of bits that can fit in the grid, and then finally, then the next block is something called bit interleaving. Okay, so the reason for bit interleaving is this. Okay, so what? Let me just share you my screen, and I can explain in just 1 minute. Okay, so let's take a small example. Okay, so what did we do? We have this bit of we have this bits, multiple bits from 0 to n minus 1 bits, so n bits. Okay, so this you map to constellation points. Okay, and then you put this in the resource grid. Suppose you put in the resource grid, you give all of them the neighboring REs. Okay, this is the resource grid. Okay, resource grid frequency. I'm just looking at one symbol. Okay. Then what happens? Suppose a deep fade occurs, like a deep fade occurs. So the deep fade occurs, and all these bits were lost, all the symbols were lost, were in error. Then what would happen? This would translate to a big chunk of bits in this going into error. Okay, so all these bits would have been gone into error. This would have been okay. So and then when you pass it through your LDPC decoder with these errors, these are called burst errors. Okay, so burst error means a bunch of bits which are close by completely go for a toss. Okay, in this particular case, LDPC decoder might not be able to recover the errors. Okay, so you understood? So if the close by bits are mapped to the same constellation points and they're put together in the resource grid, if there's a deep fade, that whole set will be gone and the whole set of bits will be gone, one close by burst of bits, and the LDPC encoder will not be able to, LDPC decoder will not be able to recover. Okay, so what they do is,
when does retransmission occur, sir?
Okay, so retransmission, this is not even involved with the retransmission. Okay, Vijay?
Yes, sir.
What was the question? Can you tell me?
No, if we lose the bits, then again it asks for retransmission.
So when I say lose the bits, means essentially these bits are most probably an error, and you pass it through. I'm not even talking about retransmission here. Okay, I'll tell you about retransmission later. So what I'm trying to say is, LDPC decoder may not be very good with burst errors. Okay, so if on the other hand, if the errors were spread out in the LDPC code word, so this is what you receive. Suppose the error was here, somewhere here. It's spread out like this, LDPC will perform better. Okay. On the other hand, if all the errors occur in one set of bits which are close by, then what happens is the LDPC will not be able to decode. Fine. So that is why what they do is, okay. So that is why what they do is they interleave the bits. What do they mean by interleave the bits is, so now you have a bunch of bits that are coming. So you have a bunch of bits from the code block after rate matching. Okay, so they write the bits like this. They put the bits like this. Okay, they put the bits in the row wise. And the output they so they put the bits column wise. I don't know this is the right direction. I don't know. This is writing it row and reading them as columns. Okay, they read it like this. Okay, and then the receiver will do the inverse of it. Okay, with this, what happens? The close by bits in the LDPC encoder will now be moved all around the code block. Okay, does it make sense? Okay, and what is the size of this grid? The size of this grid is the number of rows is equal to QM. QM is the modulation size. So if you have a 16 QM, the number of rows will be 4. So you write your entire code block in some number of columns cross 4 rows. Okay, so you write row wise and read column wise. Okay, this is called bit interleaving. Okay, and the reason why you do bit interleaving is it helps avoid burst errors. So finally, after you do your bit interleaving, then what you do is you concatenate all the code blocks. Okay, you put them all of them together. Together, and the output size will be G. This is exactly what fits into your what you say in the resource grid. Okay, that's what we saw. Okay. So what did we do till now? Till now we had MAC TBU, MAC PDU. We did TBCRC, then we did code block segmentation, CBCRC, then followed by LDPC encoding, rate matching, interleaving, and finally concatenation. Okay, so now all the bits are prepared. So this is when then we do modulation and scrambling. So now we look at these blue blocks. Okay, any questions till now? Okay, so the things that you should remember is each transport block corresponds to one UV. For each UV, at most there can be 2 transport blocks per slot. Okay.
What is code block group also? I think we have it has been introduced CBG code block group.
Code block group I will tell you when we do HARC. So what happens is, just a short 1 minute deviation. So when you go into an error, so essentially you transmitted something. Okay, you transmitted something. The receiver received. There are two ways of doing error handling. Okay, so if one of your code block goes wrong, then the UV can ask for retransmission of the entire transport block. That was what was happening in LTE. Okay, that is one way. The other way is the UV can tell the base station that this code block has gone in this transport block has gone into error. Okay, basically your encoding is over code blocks, na? So it can tell that. Then the base station can transmit only that code block. That's very good because you're using less number of resources in the transmission. Okay, but what is the problem with that is each code block, there may be some 20 code blocks in each transport block. So the feedback that the UV has to give to the base station will become large. So what they said was, instead of giving feedback on one code block by code block, they will arrange them in code block groups. Okay.
But and we have not represented here, na code block group.
Code block groups comes only HARC.
Okay.
Okay, here only code blocks. In this path, only code blocks will be there.
That is my question. Only this question.
Yeah. Code block groups come as a logical thing in HARC.
In HARC. Okay.
Yes. Okay. So now let's do scrambling, modulation, and layer mapping, and then that will give us a nice way to go into MIMO. Okay. So the next thing that is done by the physical layer is called the scrambling. Okay. So the main reason to do scrambling is, scramblers are there in every communication system. The main reason for that is, if suppose you send the same data again and again and again. Okay, suppose you send the same data again and again, what happens? The same concentration point gets picked up, and there's no change in your data. Okay, which is very, very bad for a lot of synchronization algorithms, and it will also give you DC components. Okay, so what they do is they take this bit sequence and scramble it with a pseudo-random sequence. Scramble means they XOR the input bit sequence with a known pseudo-random sequence. Okay. Because of this, what happens? You don't see a continuous set of ones or continuous set of zeros. Okay, there is some randomness in your data which is going into your modulator. Okay, that is the main reason why scrambler is used. So scramblers are present in every communication system. Okay, 5G is not only the thing. Okay, so essentially,
and the same scrambling code is required to be known to the receiver also.
At the receiver also, sir. Yes. Okay. So what they do is they scramble the code using something called a gold sequence. Okay. So I'll show you the gold sequence that they use. Yeah. Okay, so this is the sequence that they use. Okay, we will do the sequence again in detail when we do DMRS. So for now, what you should remember is each sequence has something called an init seed value, C init. Okay, the sequence that is generated depends on the seed value. Okay, so what they do is this init value depends on the particular UV identity, NI, something called data scrambling identity, and NRNTA. I'll tell you about what is RNTA in a minute, and whether it's first code word or second code, first code block or second code block. Okay, whether it's first code block, transport block or second transport block. Okay, so the C init is determined, and the C init, the same C init can be computed by the receiver. Okay, so it also generates the same sequence and XORs the received sequence so that it can unscramble the thing. Okay, so what is this RNTA? You go on seeing this RNTA. RNTA is called the radio network temporary identifier. Okay, so we already saw this RNTA when we did patch. Okay, so there are multiple RNTIs, and depending upon what is the transport channel and what you are using, a particular RNTI you use for that particular UV. Okay, again it's a MAC level thing. We don't talk too much about this in the physical layer. So essentially every UV for its data path will be associated with a particular RNTI, temporary radio network identifier. Okay, so we do that. So essentially the CRNTI, for paging and other systems, we use PRNTI. We already saw SIRNTI when we did patch. Okay, RARNTI when we did patch. So similarly, there are multiple RNTIs, and each of these RNTIs have certain range. Okay, the RNTI will be known both the transmitter and the receiver. It's a predetermined thing. Okay, so they use this combination of RNTI and cell and something called as data scrambling identity to find the C init and use it to scramble the data. Okay, so that is this particular thing. So next thing after scrambling they do is modulation. Okay, this modulation is we all know what it is. So there is QPSK 16 QAM, 64 QAM, and 256 QAM. There's also this is the downlink. I'm just putting the downlink. Okay. So at this point you have the the constellation. Okay. So the bits are mapped into constellation. Any questions till now? Did you understand this part? Good. Okay. So then comes layer mapper. Okay, this is the first time MIMO is introduced. Okay, so we'll just look at the layer mapper and then we'll go into MIMO. Okay. So what exactly is a layer mapper? Okay, so layers, the way to think about layers are number of parallel streams of data that you want to send to a particular UV. Okay, parallel streams of data. Okay, so what happens? If you have one layer and the number of code words is 1, code words means here when they say code word is number of transport blocks. Number of code words is 1. Okay, what happens is the output of the layer mapper is equal to the input. Okay, so if you have 2 layers, then what they do is they split the data. They put the even data, symbols in one layer and the odd symbols in other layer. You see that? D0 is the input and X0 is the output. X0 and X1 are the outputs. Okay, so they're taking the even indices into one layer and the odd indices in the number of layers. Okay, so if your input size is M symbols, the output of the layer mapper will be M symbol by 2 in this particular case, if the number of layers is 2. If the number of layers is 3, what they do is they're dividing them equally. So the first goes here, second goes here, third goes here, fourth goes here, fifth goes here, sixth goes here into different layers. Okay, the number of symbols by 3. Okay? And similarly for 4 layers. Okay? So one code word can be mapped at most up to 4 layers. This is what we saw also earlier. If you require 8 layers, more than 4 layers, you require 2 code words. Okay? That is this map. So for 5 layers, you have 2 code words and they give you this mapping. Okay, the first code word even goes into 2 layers and the second code word goes into 3 layers.
That means if only one UE is there, then in that condition, if the layer is 8, so only 2 code word or transport block. If number of active subscribers are more, then it is always varying with I think 2 and 1 like that, no?
Yeah. So it's all UV based, sir.
All UE based.
UE based. Some UEs can get 3 layers, some UEs can get 4 layers. I mean, not 3 layers, sorry. 3 layers or 4 layers, and some UEs can get 7 layers. It depends on that particular UE.
Finally, it goes to the physical layer in combining all this transport block.
Yes, I will tell you. I'll tell you how that happens.
Okay.
So for now, what we did was, so suppose UE1 gets 2 layers, we know how to split the transport block into 2 layers. Similar, UE2 gets 4 layers, we know how to split the data. Okay? Fine? Any questions till now? You understood this layer mapping? So layer mapping is essentially splitting the data into multiple layers. That's all.
Sir, actually, this layer mapping comes after modulation, sir.
Yes, after modulation. So the modulated symbols are split.
So before modulation itself, this is even and odd. It will go to the modulator, sir.
No. First, the transport blocks. After you do the concatenation and the scrambling, the transport blocks are modulated.
Yes, sir.
Okay. After modulation, the symbols are split. The first symbol goes here, the second symbol goes here, and other things.
Then why? But then how we can say it's a code word? Here we are saying code word.
So after you split, it's called a code word. It's just a notation. That's all. Okay. So in the spec, they tell you what this code word. Code word. If you look at this, I'll show you this.
Is there any limitation? What is the maximum number of layers possible at UE?
Sir?
Maximum number of layers possible at
8.
UE.
Okay. So they call it as a code word to layer mapping. It's just just a notation. So first is modulated, and the modulated symbols are the complex value modulation symbols are layer map. J.
So this code word and whatever earlier you described, sir.
Yeah, they're different. They are different. They have no relation.
Okay.
It's a very bad way use of this thing.
Okay.
Okay. Then what happens? I'll just tell a short story so that we can conclude this. After you do layer mapping, each layer goes in a separate RE grid. Okay, in that RE grid, what you do is, based on where the UV is allocated resources, you map this constellation points into the different REs. Okay, that is called RE mapping, resource mapping. There is also something called as virtual resource block to physical resource block mapping. Okay, let's not worry too much about this. What they do is they actually, whatever you get till now is called the virtual resource block, and when they map to physical resource block, they do some interleaving to get more frequency diversity. Okay, so again, this is nothing to worry about in the first set of courses that we do. We don't have to worry about this. So at this point, what happens is, now you have constellation points into different layers. Each of this layer goes into a resource block, into a resource grid, and you map these points to the elements of the resource grid. Okay. Okay, now let's go into MIMO. Okay, any questions? Do you understand?
So these resource grids are sent parallelly or serially, sir?
That will become clear. I'll tell you how do you handle this MIMO now. Okay, that's what I'm going to tell you now.
Okay.
Fine. So at this point, what we have done is we got the enough data to populate the resource grid. It is the data part of the resource grid, not the pilots. Pilots will come and learn later. Okay. Fine. So now I'm going to switch on to my this thing so that we can write and tell you about MIMO. So I'm going to give a very brief introduction on MIMO. I do an entire semester course on MIMO. So we are going to do very, very small parts of those things and try to understand what is necessary. Okay. Okay. So we have learned about single antenna systems in some detail. Okay. So you have the TX, you have the RX. Again, I'm just focusing on wireless parts, okay? And you have your modulated data that comes out of here, and you put it in here, and you try to recover this thing, okay? Demod. Fine. So this is only one stream. So now the question is, so we saw the capacity of this, okay? This channel gain is H. Okay, there are lots of I'll just put the ergodic capacity. So this is called the ergodic capacity. Log 1 plus. So H is a random variable. I mean, if you let's even forget about ergodic capacity. I mean, I think we should put ergodic capacity, otherwise it doesn't make sense. Okay. So what this says is the capacity of this channel is expected value of log 1 plus H square SNR. This expectation is with respect to this randomness H. Okay. So you find you do this log 1 plus H square SNR for lots of realizations of H and average them. This is nothing but expectation. Expectation or average. Okay, so average of this quantity. Fine. So one thing, I mean, of course, is W. So what I'm putting is spectral efficiency, effectively spectral efficiency. Let's only worry about spectral efficiency. I won't write WW every time. Okay. So if you look at this expression, so this capacity of this channel, the spectral efficiency of this channel depends mainly on SNR. The only way you can increase the capacity of this channel is increasing the SNR. But one thing that you can immediately see is if you increase your SNR, the increase in capacity is logarithmic. Okay, effectively logarithmic. Agreed? So increase your SNR by you have increase in dB scale so that you can get similar factor increase in the capacity. Okay? So the question is now how can you increase your capacity without touching too much about the SNR, without worrying about the SNR. So this is where MIMO comes into picture. What you do is you have multiple transmit antennas and multiple receive antennas. Okay.
Sir, this logarithm has a base 2 or 10, sir?
So you can put anything in base 2. It is called actually they don't do 10. Either you do base 2 or base E.
Sir, it is base 10, I think.
Yeah, base 2 it is called bits per second per hertz. Base E is called nats. Okay, we can just use base 2 for simplicity. I'm just telling you it's called nats in base E. Okay. So suppose now what we are trying to do is we have multiple transmit antennas and multiple receive antennas. Okay, so we transmit some data in one set of data in the first antenna, second set of data in the second antenna, third set, I mean, so many, and so on and so forth. Mth set of data in the mth antenna. Okay, what is going to happen? This antenna, whatever you transmit, is going to get received by all these other antennas, all the receive antennas. Similarly, whatever you transmit in this antenna is going to come to all these antennas. This antenna was going to come and hit all these other antennas. Okay, so at each antenna, the receiver side, what you get is a superposition of all the transmit things with appropriate channel gains. Okay, so this can be thought of as H11, H12, H1n. Okay, similarly, this can be thought of as H21, H22, so on and so forth. Okay, so what effectively you have is you have a mixing of the data in a linear manner. Okay, so this is your MIMO channel. Okay, so here your channel is a single element, single complex number. Okay, so in a MIMO channel, how many complex numbers will be there? If you think about this, there are M transmit antennas and N receive. I mean, maybe I will not put M and N. That's a bad notation. I'll put NT transmit antennas and NR receive antennas. So MIMO channel will be of the size NT cross NR. Okay, I'll put it the other way around, NR cross NT. Okay, that is your channel H. Fine. So it turns out, so the capacity of this channel scales means at high SNR, this is how it looks. Minimum of NT comma NR into logarithmic of SNR. So if you look at this capacity scales like log SNR effectively. Okay. Whereas this, I mean at high SNR, okay, when large SNR. Okay? When I say scales like this means in terms of SNR. Okay? This scale says so you see the same logarithmic factor on both sides, but the pre-constant is different. Okay, so if you increase your, if you, for example, you have 4 transmit antennas, 4 receive antennas, your capacity will be approximately 4 times log SNR. Okay, whereas in the CISO case, it is just 1 times log SNR. Okay, so you can immediately see that having more number of antennas at the transmitter and the receiver, okay, will increase your effective capacity of the system. Okay, is this clear? You can also see now, I mean, suppose somehow you are able to remove this interference. You're able to remove this interference, okay, because of the other streams that are coming. Because of the other streams that are coming like this, suppose you're able to remove this interference. Then you'll be able to get this stream here, get this stream here, get this stream here. Okay, so effectively you'll have 3 streams of data instead of 1 stream of data here. Fine. So the question, of course, the whole challenge of MIMO is how do you remove this interference? We'll see a few techniques now. Okay. Suppose you're able to do that, you can immediately see that your capacity scales like this. C is equal to minimum of NTNR log SNR. Agreed? Any questions?
Sir, but different antennas will carry different data?
Yes, different antennas will carry different data.
Hello?
Yes, sir. Yes, sir. Hello, can you hear me, sir? Pandit, sir?
Yes, sir. Yeah, now
Yeah.
I'm hearing you, sir. Yes. Yeah, sir. So that is what, so different antenna is carrying different data, and
Yes.
then at the receiver end, that antenna will get the mix of 2, mix of 3 also.
Yes, that's what I'm trying to say. So in this particular case, there's antenna, this information are getting mixed up. The 3 different information are getting mixed up. Yes?
Yes.
So the question is, if you are able to intelligently remove this interference, these 2 you were able to cancel, then you will be able to see this. It turns out that you can do that. Okay? That you'll be able to do that. That's what I will tell you a few things on how to do that. Not too much detail, but I'll point you to enough literature also. If you are able, you can show that the best possible thing that you can do is this. That is why you get minimum of NT comma NR. Okay. Essentially, the minimum of NT comma NR is nothing but the rank of this matrix. At least the best rank of this matrix H is the minimum of NT comma NR. Okay. Is this clear? Okay, so the things that you should remember is, so this is, I am talking only about capacity, not diversity. Okay, I am talking only about capacity, increasing your data throughput. Okay, so with this idea, essentially, if you have more and more number of antennas at both the transmitter and the receiver, then what will happen is your capacity scales with respect to the number of antennas compared to a single antenna system. That's what, it's always compared to a single antenna system. Any other questions before we proceed?
Sir, in that equation, C is equal to expected value of log 1 plus H square is in R. What is H actually? H is channel impulse.
H is the channel gain. I'm assuming a channel, single flat fading channel. Okay, I'm assuming a flat fading channel, and I'm telling that this H is the gain of the flat fading channel. I
am asking because even this H value of H means whether it can be determined, means is it can we do something to increase that also?
So what I'm saying is, so at this time instance, so you have frames. So your H is changing slowly. Okay. So in this frame, your H is constant. In the next frame, again, you get a new H. In the third frame, you get a different H. Fourth frame, you get a different H. Okay. So there's some coherence time for this H. This H remains constant in this coherence time, but it's random.
Okay, sir.
It is impulse response.
It's the impulse response. Effectively, the impulse. It's a flat fading, sir.
It is the impulse response for time invariant channel. If you consider the time invariant channel in that case.
So remember the flat fading channel we have discussed. So you can think of that there's only one. There's no multi-path. There's only one fade, and that is given by this H.
Okay, sir.
Okay. Okay. So let us write in, let us take a 2x2 system and write an equation for this system so that we understand how can we write this equation. Okay. I'm just going to call this as H11. H11 is a channel from first antenna to the first antenna. H12. H21. H22 is the antenna. Okay. Suppose you're transmitting X1 here and X2 here. I want to see what is my Y1 and what is my Y2. Okay, let's write this equation. So Y1 would be equal to whatever your X1 is going in through this antenna, through this H1, I mean X is going like this, okay, that is plus this path. If you write that, it will be H11 times X1
H11
plus
X1
H12 times X2.
H21 plus X2
H1 sorry, H21, yeah, H2 should be H21, sorry. Plus H21 times X2. Okay, of course this thermal noise always, this is N1. Okay, the noise always gets added to the receiver. Similarly, you get Y2 would be equal to H22 X2 plus H12 X1 plus. Agreed? All of you are, all of you are fine with this equation? These two sets of equations, with these two equations. I will write this in a matrix. I'll write this in a matrix form. I'll write this as Y1, Y2 is equal to which one? I think I okay, that's fine. That's fine. Let's write this up.
H21.
Yeah. Is this correct? H11 X1 plus H21 X2.
Yes,
okay.
Yes.
Okay.
Yes, it is correct.
So, okay, just look at this equation 1 minute. Okay, I will then write the next equation. Okay. So, what do we have finally? We have Y is equal to H matrix, X matrix plus noise matrix. Okay. So, X is of the size NT cross 1. H is of the size NR cross NT. Y is of the size NR cross 1. Of course, and this is of the size NR cross 1. Is this fine? Everyone agrees with this? The same thing. I just denoted this as H, denoted this as my vector X, this as Y, and this as noise vector. Okay? Is this fine?
Yes.
Okay, good. So now let's ask some simple questions. Okay, suppose you know H at the receiver. Suppose somehow we figure out H at the receiver. We'll worry about that later. How we figured out H. Suppose you figured out H exactly at the receiver. Okay. So my data is X. Okay, I want to get out my X. So this was the same problem we saw. Remember that we had this Y is equal to HX plus N when we did the CISO system. Suppose we know H, what did you do? How did you get X? You said X is equal to Y by H. Yeah, Y by H. Okay. So in this particular case, what do? You do the same thing, except that you can't divide by H because H is a matrix multiplication. What you do is you multiply by H inverse. Okay. So how do you recover X? How do you recover x. Okay, the answer is you put y tilde is equal to h inverse y is equal to h inverse. This is one very simple way of decoding it. There are more complicated ways of it.
It should be x delta, sir.
Sorry?
It should start with x tilde, sir.
X tilde.
X tilde should be h inverse minus y.
I'll call this x tilde. That's a good one. Okay, so x tilde. I'll put x hat, not tilde. I'll just put an x hat. This is your estimate x hat. Okay. So this what will happen? H inverse times h would be what? Will become identity. Identity matrix into x plus h inverse n. Identity matrix sometimes is x plus h inverse n. So your x hat would be equal to this. This is equal to h inverse y. Is this fine? Okay. This is a very simple way of doing things. This is again called as zero forcing. It's called the zero forcing receiver. Okay. So what did you do? You got your H channel. You estimated the channel H, and then just effectively you divide it by H. In this case, since it's a matrix, you take the inverse of it and multiply by the inverse. Okay. Okay. So at this point, you'll be able to recover your data x hat. So once you get your data x hat, then you will pass it through your demodulator, you pass it through your constellation demapper, like similarly what you have done in the previous cases. Okay. Except that now you have two layers. The two layers are x1 and x2. So this is layer 1. This is layer 2. Okay. See, this is layer 1, this is layer 2. So you send out two different sets of layer data in different layers, but there, even though there's some mixing happening at the channel, by the channel, if you know the channel estimate at the receiver, you'll be able to separate out the layers. This is one way of doing it. Again, this is the most practical way. Let me put it that way. Is this fine? So you understood what is a layer here. No? Layer here means essentially the data, the independent data you send across each antenna. There are two layers here.
Sir, in MIMO there can be more than means there can be rectangular matrix.
Yes,
also, right?
I'll come to that. I'm going to tell you that right now. Okay, just 1 minute. Okay, so at least when there are few assumptions that we made here, I will come to that assumption that will make you think clear. Okay, so at this point, what happened? You have got two layers. Fine, is this perfect? Everyone agrees? You're able to decode your two layers. Yes? Okay. So what is the assumption that we made here? The assumption that we made here is, as Srivastava is pointing out, is that H inverse exists. Okay. So if you take a 2x2 matrix, you take a 2x2 matrix, which was H11, H12, H21, H22. Okay, suppose you take a 2x2 matrix. This is your H. Okay. When will the inverse exist? Okay, so the inverse will exist if it's called something called a full rank matrix. What does that mean? Okay, so let us understand this in a little bit simplistic manner. Okay, so I'm going to put some channel gains. Let's understand this channel gains. Okay. Suppose I do this. This is my channel. Okay, I put the values of H11, X1 is coming here, X2 is coming here, Y1, Y2. So Y1 would be equal to 3 times X1. Okay, I will change the values 1 minute. Okay, 3 times X1, 5 times.
Plus 5 times.
Okay, suppose this is your channel. For example, I'm just giving a hypothetical example. And my Y2 will be equal to 3 times X1 plus 5 times X2. Suppose this happens. Okay. then will you be able to recover x1 and x2? Both these equations are the same, na? Both these equations are effectively the same. So effectively you have only one equation. Okay, effectively you have only one equation. So if you write this as a matrix, this is not a full rank matrix. Okay, what you can say is, you can see that if you write this as a system, I mean, you can write this as, if you write it as a matrix, the columns or the rows will not be independent. Okay, let me not do that right now. So you understood? So effectively, your channel should be invertible. Your channel should be invertible means it should be full rank matrix. Okay. If you in this particular case, you will not be able to decode both x1 and x2 because the rank of your channel is 1. Rank of your channel is 1 and not 2. Okay. So this is something that you should remember. The number of streams that you can transmit through your MIMO channel is equal to the rank of the channel. Okay. Number of streams should be less than or equal to the rank of the channel. Okay. In general, always the rank of the channel will be less than or equal to minimum of NT comma NR. Okay. For any matrix of size NT cross NR, the rank of that matrix is always less than or equal to one of those, minimum of those two things. Is this clear? Did you understand this part? So essentially the channel is collapsing. Effectively, you don't have two parallel streams. The channel cannot support two parallel streams in this particular case, for this particular example. I mean, you can come up with lots of examples like this. Fine. Any questions? Okay. Let me ask you one more question. Suppose you have something like this. You have 2 antennas at the receiver and 3 antennas at the transmitter. How many layers? I mean, can you actually, first question is, can you transmit 3 layers? Okay. So if you transmit 3 layers, think about this. How many equations do you have? You will have only 2 equations, 3 unknowns. Yes. What are the unknowns? X1, X2, X3. Can you determine 3 unknowns from 2 equations?
No.
No, sir.
No, sir.
No, you cannot. You cannot. So you cannot transmit 3 layers. On the other hand, you can transmit 2 layers. And you can transmit any linear combination of x1 plus x2, A times x1 plus x2 plus B times x2. Okay, this is still 2 layers only. In the third antenna, you are just transmitting the same data as a linear combination of x1 and x2. In this particular case, if you are transmitting the second case, you have 2 equations, and similarly, you have 2 unknowns. This you will be able to decode, assuming that the rank is at least 2 cross. At least the rank is 2. You understood? So effectively, the rank. So when you have a H, which is H is a matrix norm of the size 2 cross 3. So the rank of H is less than or equal to 2 always. The minimum of M comma N or NT cross NR, NR cross NR comma NT. Okay. So effectively, the number of layers that you can transmit will always be less than the rank of H. Yeah, it's basically boils down to how many unknowns you have and how many equations you have. It's very simple, basic linear algebra in that particular case. Okay. Any other question?
Sir, what about the reverse case? That is, at the transmitter there will be 2 and at the receiver there will be 3.
Yeah, fantastic. Okay, let's do this. So there's 2 antennas here. There's 3. Okay. So x1, x2, y1, y2, y3. Okay. So first question, can you transmit 2 layers? Can you transmit
Yes.
Yes.
2 layers?
Yes, you can transmit, sir.
2 layers is yes. Yeah, 2 layers is yes. Can you transmit 3 layers? You cannot transmit 3 layers because there are only 2 antennas. It will always be effectively only 2 layers. Okay. I mean, not physically possible. Okay. So in this case, what happens is, I'll tell you this tomorrow. Technically, you receive. I mean, assuming full rank submatrices, you don't require this third antenna to decode x1 and x2. Yes. What this third antenna is going to do is, this third antenna is going to help you boost the SNR of receiver signals. Okay. Let's take a simple example. Let's take a simplest example. You have only one transmit antenna and 2 receive antennas. H1, H2. This is called the menu. Okay, one transmit antenna and 2 receive antennas. Okay. So in the first antenna, you are going to receive H1 times X. The second antenna, you're going to receive. You're going to receive H2 times X. Okay, I'm going to introduce the notion of diversity now. Let's see this. Okay. Suppose you do this. So these are random fading. Now, this channel coefficients come from because of a lot of phenomena we don't know. So what happens? Assumption. I'm always making the assumption that channel is always known as the receiver. Assumption is channel. This is a universal assumption. Always known at RX. If channel is not known at the RX, there's very little you can do. Okay. So when I say channel is known as the receiver, it means both H1 and H2 are known. What can the receiver do? Okay. So what happens? So one thing they do something called maximum ratio combining, MRC. Maximum ratio. What they do is they multiply with the conjugate. For this first antenna, they multiply with H1 conjugate and then add this second antenna, they multiply with H2 conjugate and add. Okay. So this will be equal to mod H1 square plus mod H2 square times X. So what is the use of this? What is the use of this? It turns out if these two channels are independent, okay, then most likely both of them will not be low at the same time. Okay, both of them. See, H1 can be low, H2 can be low, but the probability that both of them are low at the same time so that you don't get any signal on both these antennas, the receive antennas, is very, very low. Okay, that is evident from this. Now, so they are adding coherently, that positive values are getting added here. Okay, so the probability that they are not destructively interfering with each other, they are constructively adding because they are adding positive values effectively. And the probability that H1 square is low and both H1 square and H2 square is low is very, very low. Okay. So this is called diversity of order 2. Okay. So diversity of order 2 means essentially you have two parallel paths in two parallel independent paths in which the same data is coming. The same data is coming both on H1 and H2, but they're independent from a channel perspective. Okay. So how will the BR look? Let me draw this. So suppose you have only one channel, one transmit antenna, one receive antenna like this. Okay, H1. The BR will look like this. It will fall as 1 by SNR. The slope will be 1 by SNR. I'll tell you that tomorrow. This is SNR. This is the bit error rate. Or symbol error rate, anything you can take. Okay. Suppose now you have the second case in which you also have one more antenna, H2. Then this will fall like a little bit like this. Okay. 1 RX. This. Okay. This is called the gain that you get because of the slope. The slope will change. The slope at infinity will change. This is called diversity order 2. Diversity order 2. Diversity order. Okay. So you understood? So in this effective case, what will happen is there are two streams, there are three antennas. This Y1, Y2 will be able to decode between these two streams, and Y3 will provide the diversity for these both the streams. Okay, I will tell you how do you decode in this particular case. Okay, so now you have a 3x2 matrix. How do you invert a 3x2 matrix? You do something called a pseudo inverse. Okay, pseudo inverses exist, and I will explain you how those things we do in the next class. Okay, this is fine. I'm going to stop now. So I request every one of you to please finish your homework.